Hello, and welcome to this presentation related to continuity. In other words, we're going to consider fluid flow through horizontal pipes. Pipes can be of diverging section, as shown in the figure here, from the small diameter to the large diameter, fluid flow here from left to right, or they can be converging pipes, where fluid flow is from a large diameter to a small diameter. We will consider such quantities as volumetric flow rate and also mass flow rate. This presentation does assume you've seen a previous presentation related to hydrostatics, as some of the definitions, terminology and equations used there will underpin the work within this presentation. Here's a brief overview of the presentation. We commence with an introduction to continuity, definition, and stating relevant equations such as the volumetric flow rate, the mass flow rate, and also refer to the mass density, which is mass divided by volume, and the relative density of a liquid, which relates to the density of fresh water. These two equations were covered in the previous presentation. We then consider example 1, in which we calculate the velocity, pipe diameter and the mass flow rate of a system. Then we commence the exercises. Exercise 1, 2, 3, 4 and 5. They calculate the various quantities as outlined here. The solutions to the various exercises are briefly outlined within this presentation. The presentation concludes with some questions for you to attempt at your own pace. And here are the approximate start times related to the various sections contained within the presentation to hopefully aid your ease of access through the presentation. But please note the times are rounded to the nearest minute. Let's consider the equation of continuity related to fluids. In the solution of engineering problems involving flow of fluids, which includes liquids and gases, it is useful to assume the following. Firstly, that the fluid is an ideal fluid, so has no viscosity, that is, no internal friction in the fluid. Secondly, that the mass flow rate, usually denoted as m dot in kilograms per second, is constant. In other words, the amount of fluid passing a given point in our pipe per second remains the same. We also assume that the fluid is in steady flow. In other words, the flow pattern and the velocity of the particles in the flow do not change with time. In other words, for a constant section pipe, the flow is streamlined and the velocity is constant as time increases. Note also for steady flow, the mass density of the fluid would also be assumed to remain constant. So for reference, just be aware that there are two types of fluid flow. The steady flow, also termed streamline or laminar flow, and turbulent flow. However, for this continuity presentation, we're only considering the steady flow, the streamline flow. And that occurs when the particles within the fluid move along in layers, as shown in the diagram on the right hand side here. And successive particles passing any given point in our horizontal pipe has the same velocity. So although this presentation considers horizontal pipes, we will find that the pipes have varying section along their lengths. So here's a brief illustration of fluid flow through what's termed a horizontal venturi. This was actually an experiment to confirm Bernoulli's equation, which is beyond the scope of this presentation, but it just shows using the venturi the various sections we'll consider. So notice section 1 shown here, section 2 shown here, and section 3 shown here. So between sections 1 and 2, the venturi is what's termed converging, and between sections 2 and 3, the venturi is diverging. And we'll consider this type of characteristic within the problems we're going to review within this presentation. Equation of continuity continued. So let's now consider a fluid flowing through a pipe of varying section as shown in figure 1. Here's figure 1. If the flow is steady, then the mass flow rate, denoted as m dot, across any two sections is assumed to be constant. At section 1 shown here, we'll let the area be A1, denoted here, and the mean velocity of the liquid past this section is V1, denoted here. For continuity, then the volume of liquid passing the section per second is given by the equation for volumetric flow rate, symbol Q dot, and that's simply the cross-sectional area of the pipe at section 1 multiplied by the velocity of the pipe at section 1. And volumetric flow rate has the unit of meters cubed per second. To calculate the mass flow rate, usually denoted by symbol m dot, then that's the mass density, symbol rho, multiplied by the volumetric flow rate, q dot. Or the mass flow rate can be written as rho multiplied by A1 multiplied by V1. The SI unit of mass flow rate is the kilogram per second. Just note for reference that the mass density of the liquid is assumed to be constant as it flows from section 1 to section 2 of the diagram here. Equation of continuity continued. If we now consider section 2 of our pipe, section 2 shown here, now this is considered a converging pipe, so the diameter at section 2 is smaller than that at section 1, so the cross-sectional area A2 is less than the cross-sectional area at section 1. Now for continuity, we assume mass flow rate m dot is the same at section 1 as it is at section 2. We know that mass flow rate is mass density multiplied by the volumetric flow rate q dot, or we can write that as mass density multiplied by the cross-sectional area of section 2 multiplied by the velocity of the fluid through section 2, labelled V2. Again, mass flow rate has the unit of kilogram per second. So hence, for continuity, we can write the equation of A1V1 is equal to A2V2, where the product of AV of any section will be constant throughout the pipe for continuity. So the above is called the equation of continuity, and it applies to any incompressible liquid that can be considered to have steady flow. And that's the underpinning principle of the work we're going to review in this presentation. Equation of continuity continued. And just note for reference, within the problems we're going to consider, we will either have a converging pipe or a diverging pipe. And in a few instances, there may be a pipe that converges and then diverges. So it might have 3 sections. But note for reference that a converging pipe, as shown in the figure on the right hand side, will have a diameter at section 1 and thus an area at section 1 greater than diameter at section 2, so the area at section 2. A diverging pipe has the area at section 1 less than the area at section 2. So that's just for your reference, because we'll be referring to converging and diverging pipes throughout the rest of the presentation. Let's consider a brief comparison between liquids and gases. So density of a liquid is assumed to be constant as liquids are considered to be incompressible. In other words, their density does not change under pressure. The previous continuity equations apply to gas flow, except that gases are compressible at fairly low pressures, and so density changes can occur. However, at high pressures, gases may also be considered incompressible and so have constant density. For example, the air at intake to jet planes, even at speeds well below the speed of sound, is almost incompressible, and more so gases in the exhaust jet streams of planes and rockets. So again, that's just for reference. Here are some useful conversions that we'll require within some of the problems we're going to consider. So for reference, note that 1 meter cubed is equivalent to 1,000 litres. The mass of 1 metric ton is equivalent to 1,000 kilograms, also equivalent to a megagram. And sometimes we'll need to convert mass flow rates, the m dots, between the ton per hour and the kilogram per second. So here's the m dot conversion. We're given a mass flow rate having the unit of ton per hour. To convert it to the unit of kilogram per second, we multiply by 1,000 and divide by 3,600. And conversely, if we want to convert a mass flow rate from the unit of kilogram per second into ton per hour, then the conversion used is multiplied by 3,600 divided by 1,000. If it helps you with your understanding of those conversions, I've shown some unity brackets here that are often used to help structure conversions between various quantities. So here's the unity bracket conversion from meters cubed to litres, from the metric ton to the SI mass unit of the kilogram. And here are the unity brackets for ton per hour to kilogram per second, and from kilogram per second to ton per hour. I've also shown the conversion from the unit of litre per minute into meter cubed per second, as that conversion is sometimes required within calculations. There is a separate presentation related to the use of unity brackets if you want further information on how they're constructed and used. But hopefully this slide helps underpin the work we're going to consider in this presentation. Let's consider example 1. So citric acid having a relative density of 1.659 is being pumped along a length of diverging pipe where the inlet diameter is 60 millimeters. If the outlet velocity is 2.5 meters per second and the volumetric flow rate is 20 liters per second, we've got to find A, the inlet velocity, V1, B, the outlet diameter, D2, and C, the mass flow rate, m dot, in the unit of ton per hour. Let's think through the solution process. So here's example 1 with the solution generically outlined here. On the left hand side we have a summary of the formulae associated with analysing continuity problems. And on the right hand side here we have the proposed solution sequence. So for part A we have to calculate the inlet velocity labelled V1. In the question we're given the inlet diameter 60 millimeters, so we have D1, and using this equation from our summary we can calculate the value of A1. A1 being the area at the inlet of the pipe. As we're given in the question the volumetric flow rate Q dot, actually stated here in terms of litres per second, we can use this equation from our summary to find V1 by simple rearrangement. So that's the solution for part A. Let's consider the solution for part B, where we have to find the outlet diameter, labelled D2. Now note in the question we're given the outlet velocity V2, that's stated here, meters per second. So again, using the equation Q is equal to AV, extracted from our summary, we can rearrange to find the area at the outlet labelled A2. We need to find the diameter, so we're going to use this equation, area is equal to pi d squared upon 4, again extracted from our summary, and we're going to rearrange this equation to find diameter D2, the diameter of the outlet. So there's the proposed solution for part B of example 1. And finally part C, we have to calculate the mass flow rate, symbol m dot, in tons per hour. Now in the question we're given the relative density of acetic acid, it's stated here, 1.659. So using the equation for relative density, that's the density of our substance divided by the density of fresh water, extracted here from our summary, we can rearrange to find the mass density of our acetic acid, in this case our substance. We already know in the question we're given the volumetric flow rate Q dot, so using this equation m dot is equal to rho multiplied by q dot, again extracted from the summary. We can calculate the value of the mass flow rate m dot, but that will be in kilograms per second. We will need to then finally convert m dot to tons per hour. We reviewed the conversion previously. So that's the solution to part C. I would now encourage you to start the presentation and attempt example 1, following through this outline of the solution shown here, but I will show the full work solution on the following slides. So example 1, here's the beginning of the solution. As always, the start of the process is to extract information from the question, change values to appropriate units as required, and undertake some underpinning calculations. So from the question we know that the relative density of the acid is 1.659. I've instantly calculated the mass density of the acid rho. So it's simply 1.659 multiplied by 1,000 kilograms per meter cubed is the density of fresh water. So the mass density of the acetic acid is 1,659 kilograms per meter cubed. We're given in the question the inlet diameter, D1, that's 60 millimeters, and I've converted that immediately into meters, 0.06 meters. We're given the volumetric flow rate in the question, Q dot, that's 20 litres per second. I divided the value by 1,000. That converts the volumetric flow rate into meters cubed per second. Remember, our conversion is 1,000 litres in 1 meter cubed. So the volumetric flow rate is 0.02 meters cubed per second. Because diameter D1 is given above, I can now work out the cross-sectional area of the inlet, that A1 here. And I'm using the equation pi multiplied by D1 squared divided by 4. Inserting the diameter in meters from above, that evaluates to a cross-sectional area of 2.827 times 10 to the negative 3 meters squared. We're also given the outlet velocity of 2.5 meters per second, so I've labelled that as V2 here, 2.5 meters per second. So there's the information extracted from the question. So example 1, solution continued. From reading the question, we have a diverging pipe to consider in this problem, where the inlet diameter at station or section 1, labelled D1 here, is smaller than diameter D2 at the outlet, labelled as section 2 here. So part A, we're asked to calculate the velocity at inlet, labelled V1, it's an unknown here. So part A, we're asked to calculate the velocity at inlet, section 1 here, and this velocity is labelled V1. So from the volumetric flow rate equation, labelled Q dot, the volumetric flow rate was given in the question, and that's equal to the area at the inlet, A1, multiplied by the velocity at the inlet, V1, we're trying to find. So rearranging for the velocity at the inlet, V1 is equal to Q dot divided by A1. Inserting the values, then the velocity at inlet V1 is 7.07 meters per second to 2 decimal places. Solution continued. Part B here, now going to calculate the diameter at the outlet, labelled as D2, shown here. Again, from the continuity equation, Q dot at the outlet is equal to A2 multiplied by the velocity at the outlet V2, so we're given in the question. So rearranging for area A2, in other words dividing both sides by V2 here, that's Q dot divided by V2. Inserting the values, then the outlet area A2 is 0.008 meters squared. And from the cross-sectional area formula for a circle, A2 is equal to pi, in this case D2 squared divided by 4. So rearranging for D2, in other words multiplying both sides by 4, dividing both sides by pi and then square rooting, we end up with the equation square root of, in brackets, 4A2 divided by pi. Inserting the value of A2 and evaluating. Outlet diameter D2 is 0.1 meters or 100 millimeters. Example 1, solution continued. In part C, we've got to find the mass flow rate as m dot. We're given in the question q dot, which for continuity must be the same through section 1 as section 2. So to find the mass flow rate, m dot is equal to the mass density of the acid, 1659 kilograms per meter cubed, multiplied by the volumetric flow rate, q dot, of 0.02 meters cubed per second. So the mass flow rate evaluates to 33.18 kilograms per second, and converting that into tons per hour, we multiply the 33.18 by 3,600 and divide by 1,000. We outlined this conversion previously in the presentation using unity brackets. So the mass flow rate can also be stated as 119.4 tons per hour. So that's the end of the solution for example 1. So the next part of the presentation is going to outline various exercises, but the full work solutions are included in the presentation. They will just be very briefly outlined. So here's exercise 1. In a wind tunnel, the air density is 1.2 kilograms per meter cubed, and the air passes through a converging duct just prior to what's termed the working section, that's the outlet. The air velocity entering the converging duct, the inlet, is 25 meters per second, and the duct has a diameter of 618 millimeters. If the speed of flow in the working section is to be 75 meters per second, we've got to calculate A, the volumetric flow rate, q dot, in meters cubed per second and also liters per second. Part B, the cross-sectional area of the working section, the outlet. Part C, the pipe outlet diameter. And part D, the mass flow rate m dot, both in kilograms per second and tons per hour. Answers to part A, B and C are shown in the bracket here. I would encourage you to start the presentation and attempt exercise 1, but the full work solution will be shown on the following slides. And again, if it helps, here's a summary of the formulae we are using. Exercise 1, commencement of the solution. Note the question states this is a converging duct, so the inlet diameter D1 will be greater than the outlet diameter D2. I'll let you review this solution at your own pace. Here we're extracting the information from the question and calculating the cross-sectional area of the inlet, A1. Exercise 1 solution continued. Here we're calculating part A, the volumetric flow rate, q dot. So the part A solution, q dot is given in terms of meters cubed per second and also liters per second. And part B, we're calculating the cross-sectional area of the working section. Don't forget the working section is the outlet here. So part B, we're using the continuity equation to calculate the A2 value. So area 2 shown here, 0.1 meters squared. Exercise 1, solution continued. Part C, we've got to calculate the outlet diameter. Part C shown here. So we know from the previous slide the area of the outlet. We're simply going to rearrange the formula here for D2. So multiplying both sides by 4, dividing both sides by pi and square rooting both sides. D2 is equal to the square root of 4a2 divided by pi. Inserting the values for the area from the previous slide, we calculate the outlet diameter D2 in both meters and stated in millimeters. Part D, we've got to calculate the mass flow rate, m dot. So part D, shown here, m dot is equal to the mass density, symbol rho, multiplied by the volumetric flow rate, q dot. Inserting the values, we've got a mass flow rate of 9 kilograms per second, which has also been converted here into a mass flow rate of 32.4 tons per hour. Here's exercise 2. I'm going to let you review this at your own pace. Just notice some terminology used here. This is a water supply system, and what's termed the main supply pipe is actually the inlet, and this is connected to a tributary pipe, which is actually the outlet. And there's a tapered connector between the inlet and outlet. This will actually be a converging pipe section. As I say, I'll let you read the question at your own pace. There are 3 parts to the question. For the water supply system defined, Part A asks us to calculate the volumetric flow rate. Part B asks us to calculate the mass flow rate. And Part C wants us to calculate the diameter of the outlet pipe. The answers are shown in the bracket here. I'd encourage you to stop the presentation and attempt exercise 2, but the full work solution is shown on the following slides. Here's our summary of formulae to refer to, which may help you construct your solution to the problem. Exercise 2, commencement of the solution. Essentially, we're extracting the information from the question here, and I have calculated the cross-sectional area of the inlet, denoted as A1, because I'm given in the question the diameter of the inlet, D1, stated here. Exercise 2, solution continued. So part A, we're calculating the volumetric flow rate, Q dot, calculated here in meters cubed per second. And part B, we're calculating the mass flow rate, M dot. M dot shown here in kilograms per second. Exercise 2, solution continued. Part C, we're asked to calculate the diameter of the outlet pipe. So using the continuity equation, we're first of all going to calculate the area of the outlet pipe, that's A2, it's determined here. And of course A1V1 here is actually the volumetric flow rate Q dot calculated on the previous slide. Knowing A2, and knowing that the area is equal to pi d squared upon 4, we can rearrange the equation for the outlet diameter, labelled as D2 here. So D2 is 0.306 meters or 306 millimeters. I'm now going to briefly outline exercise 3 and show the accompanying solution. So exercise 3, a length of pipe running full of oil has relative density 0.9, varies in diameter from 50 millimeters to 30 millimeters. So this is a converging pipe. If the volumetric flow rate is 420 litres per minute, we're asked to find the mass flow rate and the velocity of the oil at the inlet and outlet sections. The hint in the question is to state litres per minute into litres per second and then into meters cubed per second. Answers are shown in the square bracket here. I'd encourage you to stop the presentation and attempt exercise 3, but I'll very briefly outline the full solution on the following slides. For exercise 3, here's the beginning of the solution. Note the conversions here from litres per minute to meters cubed per second. Calculation of the areas at the inlet and outlet sections, and also converting the relative density to a mass density, shown here. Exercise 3, solution continued. Here's what I've termed as part A, calculating the mass flow rate. We calculated the mass density and the volumetric flow rate in terms of meters cubed per second, so we can determine the mass flow rate in kilograms per second. Exercise 3, solution continued. And from knowing the volumetric flow rate and the areas at the inlet and outlet sections, we can calculate the velocities at the inlet and outlet sections. So that's the full solution for exercise 3. Exercise 4. I'll let you review this at your own pace. Extract the information from the question very carefully. This actually is a 3-stage analysis where we have 3 sections of the pipe to consider. We're basically asked to determine the flow velocity at each section and also the mass flow rate. So there are 3 velocities, section 1, section 2, section 3, and our mass flow rate. I'd encourage you to start the presentation. Initially sketch the variations in the pipe outlined in exercise 4. Then using our summary of equations, here's our summary of formulae to refer to. Think through the solution to find the velocities and the mass flow rate. I will show you the full work solution on the following slides. Exercise 4, here's the commencement of the solution. Here's a sketch of the pipe showing diameter D1 at section 1 here, diameter D2 at section 2 here, and diameter D3 at section 3 here. Notice between sections 1 and 2 we have a converging pipe, and between sections 2 and 3 we have a diverging pipe. Note when extracting the information from the question, the volumetric flow rate Q dot was stated at 400 litres per second. That's been converted into meters cubed per second for our calculations. The mass density of the oil was also given in the question. So that's the information extracted from the question. In this slide we calculate the cross-sectional areas at A1, shown here, A2, shown here, and A3, shown here. Exercise 4, solution continued. So here's part A, we're calculating the velocities at each of the sections. Velocity at inlet, given here, velocity V2, calculated here, and velocity V3, calculated here. All calculated using the volumetric flow rate equation. In exercise 4, solution, this is part B. We're calculating the mass flow rate, the m dot value. We have the density of the oil given in the question. We calculated the volumetric flow rate, so we can determine the mass flow rate. And here's exercise 5. Again, I'll leave you to review the question at your own pace. We have to calculate the volumetric flow rate and the velocities at the inlet and the outlet. Answers shown in the bracket. The full work solution will be shown on the following slides. Exercise 5, beginning of the solution here. Notice the mass flow rate was converted initially from tons per hour given in the question into kilograms per second. Assumption made here is that the mass density of water is 1,000 kilograms per meter cubed. Exercise 5, solution continued. Part A is the volumetric flow rate, knowing the mass flow rate and the mass density of water. We can find the volumetric flow rate, Q dot, m dot divided by rho. So Q dot is in meters cubed per second. Notice in this case the horizontal pipe is diverging, as shown in the diagram. Exercise 5 solution continued. Here's part B, calculating the velocities at inlet and outlet. So from the continuity equation, we can find the inlet velocity V1 and the outlet velocity V2. And finally, we'll leave you with some tutorial questions to attempt at your own pace. Here's question 1 and question 2, and the answers are shown in the brackets. And here's question 3 and question 4, and again the answers are shown in the brackets. I hope this presentation has been of interest to you, and thank you for viewing.